Howdy, Solar District Cup. We are Aggie Solar Wave from Texas A&M, and we're going to talk over our design for the University of Washington. So first, about us. Slide. There we go.
Oh.
There we go. So first, about us. We're a team from Texas A&M. We represent a student organization called Aggie Create, an engineering project organization, and we were introduced to Solar District Cup through them. We also held help from Larson Lodell, from NREL, and for this competition, we just divided up the individual components from the proposed based on each person's interests and skills. And I'm Matteo Berzini, a junior in electrical engineering and the team lead for our project.
Hi, I'm Jonathan Reese, and I'm a sophomore electrical engineering student, and I led the conceptual design process.
I'm McKenna Smith, a freshman mechanical engineering student, and I led the research of the electrical systems.
Hello, my name's Amelia Vega, and I led our financial analysis. I'm a senior in chemical engineering.
Hi, I'm Caden. I'm a freshman in mechanical engineering, and I led the development plan.
Okay, so our team was assigned the University of Washington as our district, and the University of Washington's main campus, located in Seattle, Washington, is home to around 50,000 students. The university utilizes over 500 buildings that span across 807 acres, and as a whole, UW is working towards reducing their carbon footprint and improving sustainability on their campus. Two of their main energy-related goals are 15% lower energy usage by 2025 and a 45% reduction of greenhouse gas emissions by 2030, which are both laid out in their Sustainability Action Plan. And UW Solar is an organization at UW that is committed to planning and designing solar-related projects across the campus, playing a large role in the progress of the sustainability plan of the university. And so this is a map of UW, and in the center there, we have the Hans Rosling Center for Population Health, which will have energy supplied to it by the solar panels that we would like to place on top of the building. And then on the right side, we have lot E18, which is where we are proposing the construction of solar panel carports to take advantage of the open space and to supply energy to the grid that can be distributed to nearby buildings. And then here we have a table with an overview of the production and cost of the PV systems, which we will go over more in detail in the financial analysis.
Now to the specifics of our system. The two sites we strategically determined were most efficient are Lot E18 parking lot and the Hans Rosling building. The Lot E18 system will have 9 carport sections with 250 solar modules in each section. We chose this location because of the wide range of open space and limited shading. Also, there are plans for expansion in the upcoming years. Next, the Hans Rosling building has a south-facing roof that includes 300 solar modules. These additional modules are add-ons to current solar panels already installed on the roof. We carefully went through the list of buildings and systems provided to us in the district use case. Each of these sites had significant cons that prevented us from selecting them as our true system. After listing the pros and cons of each building, we were able to come to a firm decision that our current systems produce the greatest yield.
So the first proposed PV system will be a carport in the E18 parking lot. This system will generate an estimated total of 1,113,680 kilowatt hours of energy per year. As shown in blue, the section model creates the ability to expand the current system. So the parking lot also offers high solar access with an average total solar resource fraction of 99% and an average solar radiance of 1,420 kilowatt per meter squared per year. Finally, the carports were optimally positioned. The panels will be tilted south, which was determined by varying the tilt angle and plotting the corresponding annual productions. The row spacing was also between the ports will also be 22 feet to avoid shading from carport to carport. Here, a 3D model of the carport was designed to allow the university to manufacture their own carport without having to purchase them from a third party. This will allow the university to have the opportunity to save money and potentially adjust the design to fit the university's architecture. Here, our second proposed system will be located on top of the Hans Population Health Building, which generates an estimated 130,317 kilowatt hours of energy annually. The system uses 2 combiner boxes and 2 3-phase inverters to connect the 300 modules placed on the roof. This roof of this building offers high solar access, just like the E parking lot, with an average total solar resource fraction of 92% and an average solar radiance of 1,330 kilowatt hours per meter square per year. These values were comparable to the Berkeley Museum and the Merkur Court B building. However, because of the already installed solar panels, the current infrastructure of that system could be used to reduce the cost. This might include utilizing the combiner boxes or the inverters that the current system is currently using. So similar to how the panels in the carport are optimally placed, the panels of the Hans building will face south with a tilt angle of 15 degrees and row spacing of 24 inches.
Next, for the selection of our components, we chose the Longi Solar 380 watt panel, which is chosen for its high efficiency of 19% and low cost of $191 per panel and high power output of 380 watts when operated at the maximum power point. We also chose the Midnight Solar Combiner Box with the listed details. They offer both a low cost and required electrical specifications for the connections made in both the carport and the Hans building solar system. Finally, we used the Solar Edge kilowatt 3-phase inverter. This inverter was chosen for having a sufficient power rating for the output of the combiner box without having a large unused power capability, which made it possible to avoid purchasing a more expensive inverter with a higher power capability. And then here's an overview of the electrical connections in the schematics between the modules, combiner boxes, and inverters in lot E18. So 25 modules will be connected in series to form a string, and then 10 strings will be connected in parallel using the combiner box. The output of the combiner box will then be connected to the 3-phase inverter, and the output of 9 total inverters coming from the 9 carport sections will be connected inside the load center, which will be metered and connected to a 3-phase setup transformer to match the bus voltage of the transmission line. And then for the heat maps, the housing capacity near both the system sufficient, their generation is shown on the 2 maps below. If the university wishes to expand the current PV system in lot E18 by providing more carport sections, the housing capacity will be increased by incorporating smart inverter control modules to increase the power factor of the system closer to unity by reducing the reactive power of the system. And then as for battery storage, the true reasons why a battery system was not incorporated into the solar system was 1, the lack of days that the PV system overproduced the energy demand, and 2, the housing capacity near the system allowed for excess power to be distributed at the buses where the PV systems were connected, which allows a strong control of the power systems. Now I'll pass it to Amelia to talk about finances.
Okay, so let's look at the cost breakdown for each of our 2 proposed PV systems. A visual of the proportion of the cost per watt for different components is shown to the right. These costs include overhead permitting and inspection costs, installation, labor and equipment, electrical and structural costs, and of course, the inverters and our solar modules. For the Hans building roof system, the total cost is a little over $200,000. And for the carport, the total cost is slightly shy of $2 million. We've based our cost breakdown mainly on the PV system cost benchmarks from NREL, but additional calculations were made for the carport costs, while the inverter and solar module costs were sourced from manufacturers. Also note the state of Washington allows for power purchase agreements. Therefore, it would cost almost $2.2 million to purchase the total system. So another financial option was a lease. A lease structure was incorporated. The first table shows the combined monthly lease price for our total PV system, which amounts to $9,610 per month. The second table breaks down the individual lease prices for each system. And these lease calculations are based on a modeled PPA with a net present value of approximately 0 and an internal rate of return of 7.1% over 20 years. Together, these figures represent a well-balanced financial structure that ensures project feasibility and favorable returns. It's also important to note that the PV system has an expected life of 30 years, leaving 10 years of customer ownership. Let's take a look at the project incentives and net costs. For the PV system, the total cost is about 2.169 million. However, we take advantage of a 30% investment tax credit for commercial projects. And additionally, we benefit from the federal modified accelerated cost recovery system, also known as MARCS. This brings our net PV system cost down to approximately 1.4 million. It is important to note that there are no current state tax credits or incentives in Washington. Now let's examine the first-year customer savings resulting from the implementation of our solar systems. Before the installation of PV, the total electric bill was about 200,000, and after implementing our PV systems, the energy charges are significantly reduced to approximately 120,000. And in summary, the first-year customer utility savings add up to $82,215. Finally, let's take a look at the 30-year customer savings for this project. The table on the left displays the total system's PPA and IRR values along with each individual PV system. The proposed project not only hits our target IRR value of 7%, as you can see to the right, the graph on the left shows how the estimated PPA price decreases lower than the utility price later in the PV system's life. These costs are reduced to yield a total savings shown in the bottom right graphs. The calculations take into account a 3.5 annual electricity cost escalation rate and a 0.5 annual solar module degradation rate. In summary, our proposed project not only brings financial benefits to the customer, but also helps achieve environmental goals by utilizing renewable energy resources and reducing carbon emissions. And now Kaden will talk about our development plan.
As you can see, the development timeline accounts for site evaluation, permitting, inspection, financing, design, and construction. With a span of over 10 months, each component of our system was strategically placed within the timeline. Moving on to the development guidelines. We consulted the zoning and solar panel guidelines for the city of Seattle and determined that UW is placed in the major institution zone and requires a specific solar panel height limit. Using our design system, we confirmed that both systems are fully compliant. Additionally, we identified permits and inspections needed on 3 different levels, such as fire code, interconnection approval, and final evaluation. Now let's address the risks to project development. We took Seattle's non-optimal weather conditions into account within our project development. The green areas indicate extreme flood areas, and the red circle indicates parking lot E18. Some results of these risks are injuries and damages. To prevent these results, we determined some actions such as potentially constructing pathways for stormwater runoff and implementing sturdier material to our system. Furthermore, we considered the overall impact of our systems and the engagement they provide for the community. With our uniquely designed system, the energy provides a clean and efficient environment. Economic considerations such as job opportunities are also positive, with an increase in community economic growth. These impacts fall in line with the UW culture and its goals. When it comes to the engagement of the community, our system provides in-depth research opportunities that can lead to long-term education initiatives. Now onto the innovation aspect.
The innovation process of this project involved using the available data and tools, both provided and researched, along with a great focus on sustainability and different payment options for the system. Technology-wise, we have compatibility among the 2 systems, and we innovated a carport that we 3D modeled, and we also created a plan for future expansion on our proposal. And financially, we were able to create a profitable solution to achieve UW's goals and successfully hit our target IRR of 7%.
So in conclusion, we talked about our PV system on both the Hans Rosling Center and the carport E18. We talked about our conceptual system design, the financial analysis, and the development plan of our design to achieve the goals of UW. Thanks so much for having us and the ability to compete in the Solar District Cup.